We're going to start circular motion today. So before we can get into the act of actually looking at circular paths, I want to talk about what causes things to move in their particular paths. Okay, so if I want something to move in a straight line, what must have to happen to that object?
It's got to be kind of contained and flat surface.
Okay, it's got to be a flat surface. Does it start moving on its own?
You need to put a force on it.
Yeah. There has to be a force that's exerted on this object. Is it exerted at the same direction, at an angle? What do we need the force to be exerted if we want something to move in a straight line? We need the force to be exerted in the same direction as which we want the motion to go. Okay? So if I want my object to go north, I need to make the net force be in the northerly direction. Okay? We can use multiple forces if we want to move an object, right? We could both pull on something from different directions if we want it to move maybe in between us. We can make these forces, our net force, equal the direction we want to move in. Okay, does that make sense? If I want to pull on a rope from this way and Elizabeth pulls on the rope from where she's standing, there's an object in the middle, it's going to start coming out toward the middle of us. Does that make sense? So we can use multiple forces to get something to move in one particular direction. What causes an object to move in a projectile type path? Okay, if I want something to travel in a projectile path, what do I need to do to the net force? Let's think about what a projectile path looks like. Okay, yeah, maybe I throw it. It goes up like this. I need to throw it at an angle. There we go. Okay, the net force needs to be at an angle in the direction that you want the motion to go. Okay, so if I want to launch this projectile into the air, I've got to make that net force be at an angle, not just flat, not just straight up in the air, whatever. Whatever direction I need that to go, I'm going to make it go in at that particular angle. Okay, we're going to look at circular paths. So these objects in a circular motion have some of the same characteristics of projectiles. Okay. All right, so we're going to look, when we look at circular motion, at what we call uniform circular motion. Okay, what's uniform mean? The same. Yeah, good, the same. So we're going to look at things that are moving at constant speed. Okay, constant speed. If we look at speed or velocity, there's a difference between speed and velocity. Okay, velocity is a vector quantity, which means it must have what two things?
Magnitude and direction.
Yeah, good, magnitude and direction. Okay, speed, on the other hand, is just the magnitude. Okay, speed is just the number, not the direction. All right, so velocity has to have magnitude and direction. When we're looking at things that are moving in a circular path at a constant speed, okay, we have a velocity that is continuously changing. Can anyone explain to me why that is? If I have something moving in this circular path and I say it's at constant speed, but not at constant velocity, what does that mean?
It's moving, but it's changing direction.
Yeah, good. It's moving at the same speed, but it's changing directions. So as I go around this circle, okay, here's my little object moving around the circle, the magnitude of the velocity stays the same, or the speed. Okay, my direction, however, is continuously changing. Okay, that means my velocity is continuously changing. Okay, if my velocity is continuously changing, can we think of anything else that that's going to lead to? What's a change in velocity called? Yeah, acceleration. Acceleration, okay? So if I have a constant change in velocity, that means I have acceleration. Okay. Typically when we think of acceleration, we think of things doing what?
Speeding up.
Yeah, speeding up. We think of things having a change in the magnitude of velocity. Okay, we think of things that are speeding up, slowing down. They have a magnitude change. This is a directional type change when we talk about acceleration here. Okay, so in our centripetal acceleration, our velocity is changing in its directional component, not its magnitude. Okay, this is kind of what I just said, so write it down if you want. But since velocity is continuously changing, the object is accelerating. So, it'll always be constant speed, so it'll always be given, or we have to solve for it or something, but we don't have a velocity final and a velocity initial. It's going to be just one speed. Okay? So that's the little v, that's speed. Okay? Acceleration, or a sub c, is going to be our centripetal acceleration. Okay? Centripetal, anyone have an idea about what that means? Yeah? Centripetal means center seeking. Center seeking. So as this object is accelerating around this circle, the velocity is moving around the circle with it. The acceleration is pointing toward the center of the circle. Okay, it's like trying to accelerate inward to kind of stay on that path. And we could go into a lot of math to prove as to why, but we don't really need to right now. Okay, so our acceleration is center seeking, or centripetal. Okay, what do you think the R stands for? Radius. Good. The radius of the circle. Okay, and remember that radius of the circle goes from the midpoint out to the edge. Okay. So this is what our equation says kind of here in word form. So an object that moves in a circular or in a circle with a radius of r, okay, and a constant speed, which is v, has the acceleration whose direction is toward the center of the circle. Okay, so the acceleration is pointing inward. Okay, since we are moving at constant speed, as the radius of the circle increases, our acceleration must be slower, since we won't change direction quite as quickly. Okay. All right. Frequency is described as revolutions per second. Okay. When we talk about circles, what does a revolution mean?
One
Yeah, good. One time around the circle. Okay. So revolutions is how many frequency is how many revolutions something will make in 1 second. Okay, you guys have heard the term RPMs before? That means revolutions per minute. Okay, but now we're looking at revolutions per second in a little bit more of a physics setting than a car setting. So revolutions per second. It's kind of what the unit, all it would look like is that. Okay. So how many complete trips around the circle it makes in 1 second. That's what our frequency means. Frequency is little f, so it's this bottom part of our equation here. Okay, the other component of this equation is period, which is a capital T. The period is the time it takes to complete one revolution around the circle. So period is a measure of time, which is why it's a T. Okay, so when you see the capital T, you should think period. Its units will be in seconds. Okay. So if I can complete, if it takes me 2 seconds to get around this circle one time, okay, if it takes me 2 seconds, that's T. That means my frequency will then be what?
2. No.
My frequency will be, I'll switch these two places. So my frequency will be 1/2, okay? If it takes me 2 seconds to get around the circle one time, that means in 1 second I should be able to get around half the circle. Okay, do we see the relationship between those?
Yes.
Okay, period and frequency have this relationship based on this equation here, this 1 over F equation. Okay? The 1 is because we're only talking about one revolution. All right? Okay. This equation is for the circumference of a circle. Why do you think we would need to know the circumference of the circle? Or how far something has traveled. We need to know its distance. Okay? So we can find velocity based on this premise of distance over time, right? Velocity equals distance over time. Circumference right here, 2 pi r is a distance measurement. Period is a time measurement. So if we go back to our very, very basics of velocity, the very first equation we learned about velocity is distance over time. This is true for circular motion velocity. Okay? So this is another big equation right here. The distance it takes to get around the circle, the time it takes us to get around the circle one time. Okay? So 2 pi r over t. And r, again, here stands for radius. Good. Okay, so that's just explaining why we use the circumference. Okay, making one revolution is traveling around the circumference one time. All right, are we clear on this so far? All right. So these are equations for acceleration combined with velocity. You only need to know this bottom equation. I'm going to walk you through how we get there, though. Okay, so just pause for a second, let me talk, and then I will give you time to write the equation. Okay, so we're going to start here with our centripetal acceleration equation. A equals v squared over r. Okay, that was the first one we learned today. We then learned that velocity is equal to 2 pi r over t. Okay, that's the equation that we just learned, right? Are we clear so far? So since in this equation v is squared, we're going to substitute in here v into our acceleration equation. Okay, and since v is squared in our acceleration equation, we have to square this whole term. Okay, so then I'm going to take this, move it into this equation. I can drop t to the bottom, and I'll just keep the square on that, and I'll square this whole term. From here to here, I just simplified, so I took 2 squared, which equals 4, pi squared, which is pi squared, r squared over r times t squared. Okay, so this is an equation you would use if you were not given velocity, but maybe they asked you to solve for acceleration. Okay, you weren't given a velocity of any kind. You can plug this all into this straight equation, or you could just solve for velocity first and then plug it into this equation. You can do it 2 different ways. Okay, but this is one that maybe you should write down. Okay, not necessarily maybe equation sheet worthy, but depends on how often you use it. Okay, this net force here would be our centripetal force also. So you could label that F sub c if you wanted to. We're still going to take our mass times our centripetal acceleration. Okay. If we want to substitute v squared over r, that's going to allow us to use velocity or solve for velocity or use our radius if we're given that. Okay. All right, let's try one. A 13-gram rubber stopper is attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Find the tension force exerted by the string on the stopper. Okay, so before we get started here, we need to make this clear that our mass needs to be in kilograms. Okay, so we're given in grams. How do we convert from grams to kilograms? Yeah, 1,000. So it's going to be 0.013 kilograms. Period. Yeah, T. Okay, our capital T is period, so we have to call that by its name. Okay, so 1.18. We know it's the period and not the frequency because it's given in seconds. Okay, because period is a time, which should be given in seconds. What do you think the 0.93 tells us? Think about it like this. Like you're standing, holding something, and you're swinging it around like this. The radius. There we go. Okay. Okay. So how do we go about finding the tension force, right? We didn't see a force of tension in any of the equations we were given, right? Okay. So let's draw a little bit of a diagram about what's going on here. Okay. I have my circle. Here's my object. And since our acceleration is center-seeking, our force of tension must also be center-seeking, right? Because it's tension on the string. So the string goes from the outer side, out of the circle, back to the middle, correct? Right. Okay. So if I draw a free body diagram of my object, I have a tension force pulling me toward the center, and I have a gravitational force. Do I have any other forces acting on this object?
You turning it.
Yeah, that's the tension force. Uh-huh. Because I'm turning the string, which is really pulling the object. Okay. So how do we find the net force then of force of gravity and the tension force if one's horizontal, one's vertical? Not quite. Not quite.
This is what we did in the last section, or no, like last chapter.
Okay, I want you to think about whether we even need the vertical force at all.
No.
We don't. We don't, okay, because it's swung in only a horizontal circle. So we don't even need the force of gravity. That's not going to have any effect on this. Okay, it's not going to affect the tension in the string at all. Okay, so we only want the horizontal force, which would then be our net force, since it's the only thing that's acting. Okay, so force of tension here will be our net force. Okay, since these forces are center-seeking, we consider the center of the circle to be the positive direction. Okay, for just to be simple and not have to throw in negatives everywhere, the center of the circle will be our positive direction, so our force of tension will be positive. Okay? So since we know that our net force is going to be equal to our force of tension, what else do we know that will be equal to? What's that last equation that we learned? Uh-huh. Okay, so we can use force of tension equals mass times acceleration. We could also say that force of tension equals mass times v squared over r. But are we given velocity anywhere in this problem? No. So we're going to have to solve for velocity first. Okay. We could choose to plug in our whole 4 pi squared r squared over rt squared. We could do this whole substitution right here, or you can just solve for velocity first, plug in the number to this equation, which I think is a little simpler. Okay. So if we want to solve for velocity, we use 2 pi r over t which would equal 2 pi 0.93 over t, which is 1.18. Okay. Let's make sure that everyone agrees. Yeah? So we solved for velocity, we got 4.95. We're now just going to take that in and plug it in right here for our v squared. So force of tension equals mass, which is 0.013 times 4.95 squared over, what's it go over? R, good. R, which is 0.93. 0.34, good. So if this is our acceleration, what should our units be? Meters per second squared, good. Okay, so that's pretty much the extent of these problems. Okay, I threw the big one at you first. Okay, most of these problems will be much simpler than this, either just solving for acceleration or just solving for velocity. Okay, but I want you to see the entire spectrum, and then we'll break it down a little bit. Okay, so what questions do you have about this problem?
Why does it have to be in kilograms?
Why does the mass have to be in kilograms? Because that's like the base unit for mass. All right. Anything else? Okay. Let's try a little easier one. A runner moving at a speed of 8.8 meters per second rounds a bend with a radius of 25 meters. What's the centripetal acceleration? This one's easy, easy.
Wait,
If we want to find centripetal acceleration, that means we're solving for AC.
the 4 pi squared r squared, that one?
V squared over R.
So 8.8 squared.
Yep, because we were already given our velocity. So we can just plug in straight velocity. If we weren't given our velocity, then we'd have to use the 4 pi squared R squared one.
Okay.
So we can take 8.8 squared over radius, which is 25.
I like those numbers.
Yeah. So we're looking for acceleration in the piece.
It's kind of all over the place. Sometimes you'll get an acceleration and you need to solve for speed. Sometimes you'll have to solve for different forces. Yeah, it's a little bit all over the place. Okay. So what do we get? 3.1, and the units are?
Or no.
Meters per second squared.
Yep. That's what you're going to say.
Yeah, I would,
All right, any questions on this one? See, I told you they'd be easier.
That's where most of them are.
Most of them are just this 1 or 2 steps. Okay? All right.